Okay, folks, another video, another learning goal, 7.5. Know what singlet, triplet, and doublet states are, and be familiar with spin-orbit coupling. So we've already started to allude at this singlet and triplet state. So let's uncover this in a little bit more detail. So we already described the singlet state as this true paired up electron system, or anti-parallel spin state. We also described the triplet state as a parallel or non-spin paired electrons, right? A not paired spin of electrons. And it's the triplet state, right? Because both can be spin up, both can be spin down, or there's this like superposition uncertainty between the two. Well, what we haven't talked about is the doublet state, which would be a one electron system, right? So the singlet state is a two electron system. The triplet state is a two electron system. A doublet state is a one electron system because that electron can be spin up or spin down with equal probability, and we don't know which is which. So we refer to this singlet, doublet, triplet, etc. as the multiplicity. So there we have it right there. So we're going to learn a different type of configuration in this class. We're going to move very quickly past electron configuration and get into what are called term symbols. And one of the first things that we need to be able to identify in a term symbol is the multiplicity. So let's revisit these electron configurations of these common group atoms and see if we can get their multiplicities. So if I look at lithium here, and in this case, as we'll see, we're only interested in the valence electrons. Lithium has got one unpaired electron. That makes a doublet state. So now going on to beryllium, we can see it's all paired up. That has to be described as a singlet. So now going on to boron, I can see I've got one unpaired electron. That would be back to being a doublet. Now onto carbon, I've got two unpaired electrons. Those two unpaired electrons would give me a triplet state. And now, we get to nitrogen, and I don't even have a figure on here to describe what nitrogen is. So as we shall see later down the line, three unpaired electrons, all with the same spin orientation, are known as a quadruplet. So we will see that coming up soon. So now moving on to oxygen, we might think, okay, do we have some weird like pentuplet state now because we have four electrons? No, we're back to a triplet. So we're really only referring to the outermost electrons there. So oxygen in its ground state is given as a triplet configuration. Fluorine now, we've got one unpaired electron, so that is a doublet. And then finally neon, everything is all paired up. That is a singlet. And as it turns out, all closed shell atoms or ions are singlet states. Okay, so let's kind of review some about the angular momentum states of these. So when we have this possibility of the electron being spin up or spin down, the intrinsic spin of that electron couples with its angular momentum in an interesting way. It makes it so that our spectrum is going to be a direct result of that coupling. And so the energy of that interaction, which I'll call E, S, and L, is proportional to the, so that's, let's rewrite that. That looks like an alpha. It is proportional sign to some dipole moment created in this situation, multiplied by the cross product of the resulting magnetic field. So the magnetic field generated by spinning an electron. Well, as it turns out, that's proportional to the vectors S and L, and specifically it's proportional to their scalar product. So the overall magnitude is what we're interested in here. Not necessarily the direction, but we want the overall magnitude. So that's why we are interested in their dot product. So we just want a scalar result. So let's take a look. So recall when we have this vector addition, it goes as the picture demonstrates. So for example, if I have L is equal to 1, S, and really I should say that's MS, is plus 1/2 or minus 1/2, right? And we can see the resulting J vector is either then J3/2 or J1/2. So the overall magnitude of that vector, right, is given by J squared. And so putting all of that together will be the following. So the magnitude of that vector will be L plus S times L plus S, right? So I've got to FOIL it. And remember, these are vectors that we're dealing with here. So I'll end up with an L times an L. And I'm writing these out just so we can see how they all manifest. I'll end up with an S times an S, and I'll end up with an L times an S. Well, we should recognize here that this L times L, that's just going to be the magnitude of the vector. S times S is also going to be the magnitude of that vector. Oops, and I should have had a 2L times S. I shortcutted without doing the FOIL, right? So first, L times L, outside L times S, inside L times S, that gives me my 2LS. And last, S times S, okay? So, and I'm going to keep this as plus 2S times L. Well, we noted here that the energy of this interaction is proportional to this quantity. So this is the quantity that we're interested in. So I'm going to do some algebra here and rewrite these as the following. I'm going to say the product S times L equals, and just doing some algebra, 1/2 to get rid of that 2. And now that's going to be, and I'm going to write this as J squared, and then we'll have a minus L squared, and then we'll have a minus S squared. Well, if we recall, the magnitude of all of those vectors went as the following, right? The magnitude goes, in the case of J, root J times J plus 1 times H bar. So putting all of that back together, we can rewrite this as the following: 1/2 times the quantity J plus 1, minus L plus 1, minus S plus 1, all square root, all times H bar squared. Okay. So continuing along with that, we noted that the energy of interaction between S and L is proportional to that vector, or excuse me, that scalar product. So what I will do now, I'll just skip ahead and get straight to the rub here. We'll write that the energy of that interaction, the energy of L, S, and J equals the following. We'll have that 1/2. We're going to include the constants H, C to allow us to express results in terms of a wave number. And now I'm going to collect H bar squared and any other constant of proportionality we need and write it as A tilde and all times the vector magnitude quantities. J times J plus 1 minus L times L plus 1 minus S times S plus 1, all square root. So now this A term right here, that corresponds to our spin orbit coupling constant, which will be unique for each atom. Let's look at an example. So here, we've already looked at this before. This is our famous sodium D line. And what did I do here? I did something wrong with the square roots here. Oh, yes, I know what I did wrong. I don't need the 1/2 there because these were all the magnitudes squared. Okay, so let's get rid of those square roots. We don't need those, right? Because I had, this would have been j times j plus 1 square root, but then we squared it. Okay, so continuing along, here's the expression that we just came up with. So if we go back and look at the sodium D lines, right? And specifically for the transition corresponding, oops, I missed it way up here. There it is. I skipped ahead to the wrong page. I got ahead of myself. Okay, anyways, we'll just keep going with this. So if we look at this transition from the 3s1 to the 3p1, so we recognize this is a doublet state. This 3p1 level is split by the corresponding j values. Remember, j equals L plus S all the way down to L minus S. So with L equal to 1, I will have j 3/2 as the upper level and j 1/2 as the lower level, okay? So as it turns out, if we look at this spectrum, we see this doublet line here separated by roughly 0.7 nanometers. That 0.7 nanometers corresponds to 17 wave number. So the level is split by this factor 17 wave number. Well, that's not quite the value of our L or of our spin orbit splitting constant. So now if we go down here, this is where I got all confused on my slides. If we go down to this next slide here, okay, where again, we recognize we're going from 3s1 to 3p1, 17 wave number difference between that level, right? So if we plug in all of these appropriate values, right? If I plug 3/2 into here, and then I plug in 1/2 into here, and I keep it going, right? My E for the 3/2 line ends up becoming, so put that all together, right? Let's do that. So 1/2 HC times my spin orbit splitting constant. So now that's going to become 3/2 times 3/2 plus 1 is 5/2 minus, so remember my value of L for P is 1. So now that's going to be 1 times 2. So I'm just going to write all these down so we know where they came from. And of course, the value of S is always 1/2. So now that's minus 1/2 times 3/2. So if I put all of that together, do all of that math, right, then we just get positive 1/2 HCA. Okay, so I know that doesn't look too obvious, but work it out for yourself. And if we did the same thing for the J 1/2 level, this would turn out to be minus HC times the spin orbit splitting constant. So the spectra shows us that there is a 17 wave number difference between these two lines. And from that, we can work out what the spin orbit splitting constant must have been. Remember, the differences between this corresponds to delta E. So delta E of J will give me the following. So if I subtract those out, I will get 3/2 so I could say 3/2 HCA if I wanted to express my results in joules, or I could remove the HC if I wanted to keep my results in wave numbers. All the same, we can see here that 3/2 times that A constant, or really I do the algebra, right? And it would be 2/3 times the observed delta E gives me the actual spin orbit splitting constant, right? So do the algebra, and then I divided by hc, right, to get that into a wave number. So then that means for sodium, it would be 2/3 of whatever is observed. So it's roughly 11 centimeter wave numbers is the spin orbit splitting constant for sodium. And if we were to go down the line here, we would see a periodic trend. So we would see in the case of lithium, it's only 0.23 wave numbers. In the case of potassium, it's 38 wave numbers. For rubidium, it's 158. For cesium, it's 370. So we see this lovely trend going where the larger is the value of J, the more spin orbit splitting there is, which kind of makes good sense when you think about that this equation is based on the value of J. Okay, so, and we're going to see more observations of this spin orbit splitting as we continue to discuss spectroscopy. Okay, folks, I'll see you in the next one.